Hey everyone, this is part 4 of my homemade VIC-II 6567-6569 replacement project. That's the video chip that goes into the Commodore 64, and I'm looking at trying to replace it with an FPGA-based solution. So I'm happy to report that I now have a fully functional VIC-II replacement board for the Commodore 64. This is still a prototype board, which is a hat for the Mojo V3 FPGA development board. But I now have everything I need to make an all-in-one PCB for this. It's working very well. I was able to resolve the last couple of technical issues I had. I changed the board layout a bit and added some series resistors to take care of the noise issue. And I finally found out the cause of the crashes I was seeing, and you won't believe what the reason was for that. I'll talk about that a little bit later in this video. But for now, this is fully working. It's highly accurate. I don't know of any demo or program it won't handle. So far it's handled everything I've thrown at it, but there's always the possibility that there's some remaining glitch, but those can always be taken care of. It's expensive in its current form because I'm putting this together with 3 pieces. There's 2 off-the-shelf pieces and 1 custom PCB, but hopefully I can get that cost and footprint of this down by creating a single PCB. I'm also very excited to talk about some additional features that I've added to this project, so and I think it'll make the extra cost worth it. So this is how I'll be capturing the output of the VIC-II board. I've rigged it up to my VGA monitor. I can't capture either HDMI or VGA output because the resolution is not standard, so this is how I'm going to be filming it. You might notice a slight roll because the camera is at 50 Hertz, but the video output is not exactly at 50 Hertz. And you might also notice a slight moire effect, but hopefully this is good enough just for demo purposes. So I decided to name this project VIC-II Kawari, and Kawari is a Japanese word for instead or substitute or replace. So when this code finally does end up on GitHub someday, that's the project name it will likely be under. So like I mentioned before, I have good news. The noise issue that I was having before has been resolved. I added series resistors, and this is the before and after picture from the oscilloscope of what this is the clock, the CPU clock, what it looked like without any data activity, and then with data activity you can see that the noise has been greatly reduced, and so I'm pretty happy with the way that turned out. And I also discovered the cause of the crashes I was having, and it wasn't my board or noise, it wasn't the motherboard or a bad chip on the board, it was my Pi 1541. And so let me explain. It was behaving as though data was getting corrupted in memory. So I thought maybe it was DRAM refresh. I was looking at address bus contention possibilities, data bus contention. I thought noise might be the issue, the CAS-RAS timing. I was looking everywhere in my code to try and figure out why some demos were crashing. And then eventually I just had an idea to switch to a real 1541 drive because I had been using this Pi 1541 from the beginning, and surprise, I got no crashes. And this kind of explains why I was also seeing crashes on my real 6569 with the same Pi 1541. I checked the power supply, the IEC cable, I swapped Pis, and eventually I ended up, just out of curiosity, turning off the piezoelectric buzzer that's on this board, and then I was able to run many demos back to back without crashes, and I ended up running Edge of Disgrace, Comaland, Lunatico, Christmas Mega Demo 2020, the Star Wars demo, Uncensored, We Are demo, all back to back, and not a single crash or problem or glitch. So I'm not sure if this is a problem, like a general problem with Pi 1541 or this particular board that I have, but it looks like, my suspicions are that when you turn on this piezoelectric buzzer to make those drive sound noises, that there's some interference or some noise that's causing the bit stream to get corrupted when it's being delivered to the 64. And I can kind of see at certain points it was clear to me that data was just not getting either loading correctly or being corrupted after it was loaded, and it was really difficult to figure out which was the case. But then eventually I tracked it down to this issue. So Switching over to a real 1541 drive helped me isolate this, and since I've turned off that buzzer on the board, I haven't had a single issue, so hopefully that was it. So let's talk about bonus features. I added new registers, and these extension registers, they're deactivated by default, and there's this activation sequence that you have to go through before they open up. And the reason for that is I don't want existing programs to accidentally or unintentionally invoke these any of this new functionality that I've added. So you basically poke the PETSCII characters VIC-II into location D03F, and that will open up the registers D02F to D03F, which are normally they normally do nothing. But they're going to activate certain features that you'll find in VIC-II Kawari. So what do the new registers do? Well, I added 32K of RAM, and that's just block RAM on the FPGA. It's not external RAM. I'm considering upping that to maybe 64K, depends on how things go, but I added this mechanism for the 6502 CPU to read and write to that video RAM. And this is kind of similar to what you might find with the Commander X16 project. I have 2 pointers. You'll see on the right hand side there, D039, D03A are the low and high pointers for pointer 1, and D03C and D03D are the low and high pointers for pointer 2. And then you'll see that there are mem value registers. If you poke into that register, mem1 value or mem2 value, then it will essentially poke or peek into video RAM. And there are flags on that last register, video mem flags, which can auto increment or auto decrement that pointer or do nothing. And there's also an indexing mode which comes in handy if you're porting indexed in direction to use video memory. And so using these pointers, you can have the CPU can get access to the video RAM. And I added some new video modes for hobbyists to play with, and I'll describe what those are a little later. And I also enabled a 256 register overlay on top of video RAM with a flag. That's one of the video mem flags. And those 256 registers add even more functionality. So one of the first things I did is I made the 16 color palette configurable. And it's 12-bit color, so you have a 4096 color palette to choose from, and you can define the red, green, and blue values of each of those 16 colors. And there are 2 palettes that can be swapped in by just a simple register change. That's one of the registers that the CPU can access directly. That's not meant to be for preference. That's meant for programmatic changes. Currently it doesn't remember what those color changes are. I might end up persisting those between reboots, but for now, when you boot, the 2 color palettes are, one is for PAL and one is for NTSC. They're just basically the VIC colors that match as close as possible with 12-bit color anyway that I can get between those 2 schemes. But this kind of opens up the door to experimenting with certain raster line effects where you can change the color palette on the fly, per raster, or other video effects that you can't do with a genuine chip. And so I thought that was pretty neat to have a configurable palette. So this is another demo program here. This is showing what you can do with the custom palette. So this is actually a test program that I wrote that helps me figure out if I have my wires crossed on the VGA. I hope I can just cycle through different palettes. So here we're just getting shades of red, shades of green, shades of blue, and then a cross between red and green. And then you might have a grayscale. You can just basically define that palette any way you want. So another change that I made is I added a switch between NTSC and PAL modes, and it's just a matter of a register change now. So no need to open up your shell or wire in a switch. It's basically poke a few registers and next cold boot, and the switch is complete. So I just want to show you a config utility that I wrote, and this is written in BASIC, so it just uses pokes and peeks to do its thing. And what it does is it detects the version of the board that you're running, since I intend to release probably multiple versions of this. And currently you can select the chip model that you want. And so here it's set to 6569 PAL, and I can cycle through the different chip models. So we do 6567R56A, 6567R8, and then back to PAL. So those are the three chip models that it will emulate. And so you save those changes, and then next cold boot, and you basically switch the video standard of the machine. I also added this raster lines effect, which puts every alternate line at half brightness. And if I do that and save it, it makes the picture a little darker, but it kind of gives it a more retro feel. Instead of that pixel perfect look, you get, I'm not sure if it's coming through on the video here, but you get a raster line effect, and I like how it looks. But again, you might have to turn up the brightness on your monitor to match the brightness of the previous configuration. So I'll just turn that off again. And so this is going to be probably going to evolve over time as more features get added, but so far it's just a simple video standard switch and raster line configuration. And how that's working is there's on this Mojo V3 FPGA development board, and what would necessarily have to be on the final PCB is that there's a microcontroller on there, and it's responsible for loading the bit stream into the FPGA, because FPGAs are basically blank and they need to be configured with the logic. So it loads the bit stream, and there's a loader program that comes with the Mojo V3, but the microcontroller is basically the same microcontroller that you'd find on something like an Arduino Uno, and you're free to update that loader program after the part that loads the bit stream. You can do whatever you want in there. So what I did is it basically enters this slave mode, and I set configuration pins from settings that have been stored in the EEPROM memory, and then it just basically sits and listens for changes that are coming from the FPGA over a serial connection between the two devices. And so whenever you're poking registers that might change something that you want to persist, and those come across the serial connection to the MCU, it persists them, and then next cold boot you get the configuration pins set properly. So that's how that's working. Okay, and before I go to the next slide, I just want to load a small program here. And if I do SYS 51200, you get an 80 column mode for the Commodore 64, and this turned out really well. I'm happy with this. It's basically a real 80 column text mode. It's not a bitmap mode, so it's not like one of those soft 80 programs that kind of cut the cell in half and you get a smaller font. You get a full 8x8 font on every character. Every character cell has its own independent color, so you can you don't have any sort of color restrictions that you would have with those soft 80 versions, and it's also not pushing around a ton of memory, so it's quick. It's pushing around twice as much memory, so it's a little bit slower on the scroll, but not by much. I think it's probably like what you would get on a PET. So if I loaded something like the config basic program, you can get an idea of what it looks like that. And everything works like you would expect it to work from the 40 column mode. So you get like you can slow it down. It's basically a replacement for two kernel functions, the character out and character in functions, and I just basically recompiled the kernel versions with the new limits and a couple of other changes as well. Now this is using video RAM. It's not using any of the DRAM from the 64's main memory. So if I do SYS 51203, you see that it switches back to the 40 column and those 40 column mode, because those two displays are those two regions of memory are separate. You can toggle back and forth between those two modes, no problem. And it also remembers, if I go back to, say, the 40 column mode, and then say I link these two lines. I don't know if you're familiar with the 64. Every two lines when you're programming in BASIC are linked, so you can see that those two lines are linked, right? And if I toggle back to the 80 column mode, I can clear the screen, can do whatever here, then go back 51203. You can see that those lines are still linked, and that's because the code, those kernel replacement routines, they save the link table between the mode switches, and that program is only 2K. It's a small program that resides at C800, so it doesn't interfere with any basic memory. You get your full basic memory, and like I said, you toggle between the two. It's just operates just like the 40 column mode you would expect it to, but I thought that was a pretty cool feature to add to this, and I think it's something that's just like a bonus feature that's brings a true 80 column mode to the Commodore 64. So one of the nice things about the 80 column mode is that a lot of the same memory locations work. So I can, for example, poke 646, which controls the cursor color. The Shift Commodore key will do the same thing that it does in the 40 column mode. It's actually using the same register to make that switch. I can poke, say, the border color, or the middle color, or the background color. If I do control run stop restore, it goes back to 40 column mode, but then I can just toggle back to the 80 column mode. And so many of the other VIC-II registers that control things like, for example, 53270, 5327047. So that's the X scroll register. That works as well. I can do the same thing with the Y scroll. So a lot of the programming tricks that you can do in the 40 column mode, they apply to the 80 column mode. Of course, the 80 column mode is its own thing, so it's not going to behave exactly the same way, but it does share a lot of the same registers. And so another thing I did just for fun is I found the Adventureland code for the Commodore 64, and I just changed the limits from 40 columns to 80 columns. And because that program is just text adventure, you can just run it without any sort of any changes, and it'll run in the 80 column mode. And that was just for kicks. And lastly, I did add a few more graphics modes just while I was in there. It's very easy to add graphics modes. I'm not sure if these are going to stay in the final version, but I ended up adding 640 by 200 bitmap mode. That's the 16 color bitmap mode. You still have 8 by 8 color cells, so that's 2K of color, 16-bit bitmap. And then I also added a 320 by 200 16 color 2-bit plane mode. And I mean, the difference between this and the modes that you might find on the normal or the genuine chips is that you have independent control. Every pixel can have its own independent color. There are no restrictions like you have in the regular modes. And then I finally added 640 by 200 4-color 2-bit plane mode, which is a high-res but low-color mode. And those last two both take up 32K. So let me just load up one of the sample images. Image. Okay, so here's one of the sample images. This is the 320 by 200 16 color mode, but remember that the palette is configurable, so those 16 colors don't have to be the regular 16 colors that the Commodore 64 has. And so here you have a bunch of shades of green and gray, and every pixel again is can have its own separate color. There's no color restrictions. And so here is the last video mode. This is 640 by 200, 4 colors, and so you get high resolution but low colors. And I'm not sure if I'm going to keep these modes, but if I do, I think I might have to bump up the video RAM to 64K, because these modes, these last two modes anyway, they use up all the memory, and you don't have anything left to, say, flip between two frames to do some sort of double buffering technique. So either reduce the resolution or increase the memory. But I don't think I'm going to go past 64K, because I mean, it is an 8-bit machine at 1 megahertz, so you can't really push around too much memory, especially through this video memory interface that I've come up with. But anyway, that's just there for interest's sake, and if that's included, then it's just an extra bonus feature. I don't really expect a lot of use out of it. It's just really for interest's sake and for hobbyists to play around with. One thing I forgot to mention is when you're in any high-res mode, like the 80-column text mode or any of the other modes that I have, there are no bad lines in those modes, so you end up getting more CPU cycles available per frame, because the CPU doesn't have to share access with the video RAM. The video RAM is exclusively accessed by the FPGA, and that frees up, I think, something like 1,000 cycles per frame, which might translate to, depending on what instructions you use, to something like maybe 250 6502 instructions, and that's extra instructions that you can use to do work. So that's just an interesting kind of side effect from having those high-res modes. And it's kind of similar to what you get when you turn off the display enable bit in one of the 64 registers. You get a blank screen, but in this case you don't get a blank screen if you have the high-res mode activated, and you get something like a 6% boost in CPU cycles per frame. So that's kind of neat, that it would help with pushing around extra data in those modes. And so that's it for now. Next steps, I'll work on making an all-in-one PCB for this. It'll likely have to be DVI output for licensing reasons, but I will try to support DVI and then so HDMI with an adapter, and VGA as well. So the DVI output will have the digital or the analog outputs. And yeah, this project has come together pretty nicely. I'm really happy with the way it turned out, and let me know in the comments below if you have any ideas for features that are missing. I'm thinking you might want to add like a math coprocessor or something to help you do multiply, divide. Of course, these things are just for interest. There's no existing software that's going to use this stuff, but for hobbyists, it's just fun to play around with. All right, thanks for watching.